Hi, my name is Anthony Crain, and today I want to talk to you about another test topic, defect density. Previously, I talked about all the different paths of testing and why you can't test at all. Today, I want to talk about defect density, and I want to talk about what it is, why it's important, and how to use it to actually improve quality in your software organization. Okay? So, first off, I found out that a lot of people don't really get the idea of defect density. Before we go there, my favorite question to ask someone in test that I've just started to work with as a consultant is, what do you think the purpose of test is? And they always feel like they're on the spot, and I'm not going to judge them for the answer. I just need to understand where their mind is at so that we can travel together. So the most common answers I get, one is that we test to make sure something is fit for delivery. I think that's a level 2 out of 3 answer. That's actually a pretty good one, fit for delivery. That's true. We should figure out, but here's a question. How often does a test organization actually say it's not fit for delivery? And then we don't deliver after spending all this time and money building something. It seems like it doesn't happen very often. So I hear that we're supposed to test if it's fit for delivery, but do we actually have any say in that delivery? In some organizations we do. I've been in some life critical organizations where if test says it's no good, they got to start all over again, and it's a big deal. But it's still pretty even rare there. The other answer I get, at least verbally sometimes, but in actuality all the time, is we test to find a defect so that we can fix the defect, right? It's the find and fix mentality. And I see that a lot in organizations. All the testers do is they find the defects so that the developers can fix them. And the developers, they're not even ashamed anymore. They're just like, oh yeah, I had defects, I'll fix them now that you found them. What happened to the original idea of I shouldn't create those defects in the first place, right? That's called defect prevention. And we're going to talk about that a bit as well. So that to me is the worst possible answer, is that we are testing to find the defects so we can fix the defects. The mid-level answer is fit for delivery. So what is, in my opinion, the best possible answer? We are testing so that we can understand the quality of our solution and improve that quality. Now that's just too vague though, because we design so that we can improve quality. We architect so we can improve quality. So that answer is too vague. Defect density is the coolest tool to help us, in fact, improve the quality of the software we're developing. So let's talk about defect density, how to use it, and also defect prevention. My favorite way to explain defect density is an analogy that I kind of just made up one day, and like on the spot, and I've been using it ever since, and now I'll even have it on video. I call it the Mercury in the lake. Mercury. Okay, so let's imagine, and again, this is all hypothetical, let's imagine you own a lake, and you want your friends to come over and swim in the lake. You want your family to swim in the lake, everybody to have fun in the lake. But you find out that if the water has more than a certain amount of mercury in it, a certain amount of parts per million of mercury, it's actually unsafe to swim in. And let's imagine that it's 10 parts per million. I probably should look up if there's really a statistic like this, but I just made this up on the spot. I'm still going with it. Let's imagine it's 10 parts per million of mercury. Anything more than that is unsafe. Anything less than that is safe. By the way, don't think that I'm actually some kind of earth scientist. Don't go swimming in a lake, without knowing the real facts about what's safe. Okay, but for my analogy, 10 parts per million. So let's imagine that it's 10 parts per million, and you know that in your area some of the lakes have been considered contaminated. So you know it's something you need to check into. So the first question is, how do you find out if there's too much mercury in the lake and to allow people to go into it? So another way of saying it is, how do you find out if your lake is of good enough quality, right? Yeah, see, test, okay. So what do? Pausing to see if you want to think about it. You would somehow test the mercury content of the lake. Well, how do you do that? Well, you could take a scoop of lake water and bring it to a lab and say, hey, lab, how much mercury is in my scoop? And then they could say, oh, okay, well, we measured the amount of mercury in your scoop, and you have 20 parts per million of mercury in this scoop of water. And now what do? So what does this tell you? Does it tell you the exact parts per million in the lake? Well, no, it depends on where you scooped it from. Maybe near the mouth of the lake where the water comes in from the stream, maybe there's less. Maybe at the deepest part of the lake, maybe there's more, right? So you might want to take scoops from different parts of the lake to get a better understanding of how much mercury. Well, that's a lot like test theory. We have different test theories that tell us the best kinds of ways to test. I know when I was trained, I was showed about 10 different ways to think about how to find good tests, right? So the idea is finding the best tests. Well, in this case, one from the where the water comes in, one from the water comes out, one in the deepest part, one in the shallowest part. Okay, that might be an example of some test data, but in the end, you have 4 scoops of lake. You're not testing the whole lake still. All right, so in the end, you decide there's 20 parts per million of mercury in the lake. Well, even though it's just a sample, you deduce that the whole lake has about 20 parts per million of mercury as well. That's what testers are doing. We're not supposed to find defects so people can fix them, right? We're not even worried about fit for purpose if we're not even allowed to stop it from going out anyway. I mean, if we can just point out and say, hey, this doesn't do what you said, and they fix it, well, that's great. Not like we're really stopping it. But what we can do is figure out the defect density and to say, this is about how much problem there is in the software based on the sample that we've tested so far. If you don't understand that, I talked about subset testing in my other video. Why didn't you find that in tests? So go ahead and take a look at that. In the meantime, as long as you get this, in my subset, in my little jug of water, I found 20 parts per million, therefore I assume there's 20 parts per million. That's the idea of defect density. Let's keep going with this analogy though, okay? So now, let's imagine that, that we want to clean the lake, right? How do we get the lake clean? All right, give it some thought. How do you clean a lake full of mercury? Did you get it? Did you pause? Unpause? Never did? Doesn't matter. All right, so here's the wrong way to do it. So the lab, I go there and I give them my jug of water and they say there's 20 parts per million. But by the way, we removed all the 20 parts, so now this jug of water is clean. And I'm like, oh, great, this jug of water is clean. That's what it means to, when you find a defect, go fix it. All you did was clean the jug that was your test space, that was your subset of test. All I did was clean out this jug of water. Now I go back and I dump that jug of water back into the lake. This clean water with no mercury, I dump it into my lake that has 20 parts per million in the whole lake. The question is, how did that change the defect density of my lake? It probably didn't. It's still pretty much 20 parts per million. Yep, I added a jug full of clean water to the lake, but there's so much more lake than there was jug that if there was 20 parts per million in the lake and there's no mercury in my jug, I didn't exactly clean out the lake with one jug of water. So this is what we're doing when we find a defect, we fix that defect, all we do is pour a clean jug of water into a big lake. Now again, some people say, I don't believe there's that many more defects than the ones we found. You're saying that when we find defects, we find a jug worth when there's in fact a whole lake worth of defects that we didn't find. People find that very hard to believe, and that's why I use that other why didn't you find that in test video to help people understand, no, there really is a lot more defects you didn't find than the defects that you did find. So the defect density is a very critical understanding of what's left that you don't know about. So this seems really frustrating. You're like, well, great. So that means if I test my little jug, I clean my little jug, I pour my little jug back in, I haven't changed the defect density. There's still a ton of defects to the tune of about 20 parts per million, okay? So how do I clean the lake? How do I clean the code? How do I make the code better than 20 parts per million? All right. Now, think about this. No matter what the technique is, every time you sample a lake, you can see what the parts per million are at. And so you can see the effectiveness of the ideas. And that's exciting. That's why you want to know your defect density. So you can say, wow, our defect density is getting better, or wow, our defect density is getting worse, which means even in the parts we're not testing, we know it's getting better or worse. And that's the exciting part of defect density. All right, so how do you clean the lake? Okay, let's stick with the analogy. So you got a lake full of mercury, and you're like, how do I clean my lake? Root cause analysis, okay? And now we're getting into what's called defect prevention. IBM called it orthogonal defect classification, ODC. Really bizarre name, and you'll understand why they call it that in a minute. But I call it defect prevention. I think it's easier to remember than ODC or orthogonal defect classification. Okay, so we need to find the root cause. How did the mercury get in the lake in the first place? Well, there's a river that feeds the lake. Maybe that's bringing the mercury in. In fact, it's either coming from the ground itself or it's being fed in from the water. Well, a little research and we find out that partway up the river, there's a plant, a manufacturing plant, and they're dumping mercury in their little stream. And that mercury is being brought down into our lake. And in fact, that's what's contaminating all the other lakes in the area too. Ooh, look at this little bonus find that we just discovered. So now, how do we get the mercury out of the lake? We have the manufacturing plant stop dumping the mercury in. Now, nothing but clean water runs through. As the clean water runs into the lake, little by little, the mercury in the lake gets cleaned out as it goes down. And eventually, if we keep testing with the bucket, we find out that it's a 10 parts per million, then 5 parts per million, and then no mercury in the lake because it all got washed out. and all our friends can go swimming. What do? We found out what was going wrong upstream, we fixed it, and we let the code run through. We let the water run through, cleaning out the lake. So we need to do the same thing. This is what is meant by orthogonal defect classification or defect prevention. And this is, to me, a way more exciting job for a tester than find a defect so that they can fix it. This is the true job of a tester. Okay, so ready for this? As a tester, my job is to understand defect density. Then to categorize the defects. So let's say we find 1,000 defects. That's a lot of defects. That's a lot of data. What we need to do is look at the categories of defects. Okay, well, yeah, there's 1,000 of them, but there's 3 major categories. There's 8 major categories of defects. Some are this kind, some are this kind, but there's 3 of them or 8 of them or whatever the number is. There's some specific number of defect categories. Now, which category is the biggest? Well, category 3, we have more defects. 30% of all the defects are in category 3. The other, X number of categories represent the other 70%, but no one category has more than 30%. Interesting. Can we come up with a methodology change or a new tool that will help us to eliminate that category? A simple example, let's imagine that the biggest category is uninitialized variables. I know it's pretty specific and pretty small, but let's imagine, okay? So you're like, wow, uninitialized variables is the biggest source of defects in the sample, and therefore probably the biggest source of defects in the whole lake. So can we either add a process step to make sure we don't, maybe peer review or something for specifically uninitialized variables? Let's add that to our peer review process. Or maybe there's a tool that we can buy that will actually run through the software to see if there's any variables that were not initialized before use. Okay, maybe we can write a little script for that. We can automate it ourselves. In the end, we target that category. All right, here's where it gets fun. We let the stream run through. We start programming with this new tool in place or this new methodology step. And what should that do? That should start cleaning out the defects. That should start cleaning out the lake. So now, as a tester, I take a new scoop of water and I test it. And this time, not only do I figure out how many defects are there and what the percentage is, the density, but I also specifically add new testing for uninitialized variables. I really extra look for that, in addition to my normal testing. And of course, I have to back down because we only have so much bandwidth. But I look a little extra heavy for the uninitialized variables. And after all the testing is done, we found none. We found 0 uninitialized variable errors in this bucket of test water. Okay, well, what does that mean? It means you can multiply that across all the tests you don't run. That whole lake, you can assume if none of those are in the bucket, then none of those are in the lake either. You have just eliminated an entire category, and not just a category, the biggest category of defect in your software. And how did we do it? We took a defect density sample, we looked for categories, that's orthogonal defect classification, that's looking for categories across defects, and then we put an improvement in place to prevent that kind of defect from now on, okay? And then we tested again, and sure enough, we couldn't find any more evidence of that kind of defect. So now what do? We look at the categories that are left, and we look for the next biggest one, and we try it again. And by the way, the categories will change. Sometimes, as you test, you realize there's other categories you didn't think of. That's all fine. I have a starter set of categories that I give all my clients right away. I'm like, here's a starting set. You'll grow into your own, but this is a nice way to start. And in the end, you're looking for those categories. So that's my Mercury in the Lake example. I hope you now understand what is meant by defect density, how many defects you have per opportunity, right? There's actually 2 ways to measure it. It's defects per line of code. So in my bucket of water, I had 1,000 lines of code. I found 10 defects. That ratio would be your defect density. Other people do a test effectiveness metric where they say we ran 1,000 tests and we found 10 defects. So test effectiveness is an interesting metric as well. But for defect density, it's usually lines of code and then how many defects you found. Now, not everybody measured lines of code. So then you'll have to use some other proxy. Function points if you're doing those. Story points if you're doing stories. You can say how many defects per story point. You can do how many defects per use case point, right? So figure out something that can be your denominator, whether it's lines of code or anything else. And then your numerator is always the number of defects found. Okay, and then your test effectiveness is how many tests they run and how many defects found. So you can see, here's the thing, if we run a lot fewer tests, our defect density could go down. That didn't mean our quality went up. So it's important that you counterbalance defect density metrics with something else like test effectiveness. So you can say, yeah, our testing was as effective and we found fewer defects. So now I feel more comfortable that the lake is getting clean. Best way to find no defects at all, stop testing. right? And then, ooh, look, we have 0 defects. No, they're all still there. We just didn't do any testing, and so we didn't find them. So keep that in mind. So anyway, I hope you now understand defect density. I hope you understand what it means, what it's for, and how to use defect prevention and defect density together to, in fact, really improve the quality of the software in your organization. Thanks. I'm Anthony Crain, and I hope you found this useful.